Hello, higher algebra students, back here with Unit 9, Quadratic Formula, Lesson 1, Radicals and Discriminant. So today we're going to focus on this quadratic formula, first of all, which is one of the cornerstones of algebra. Really, you'll hear about the quadratic formula in a number of different areas. What we're going to look at today is in ways to solve the quadratic. So last unit we dealt with factoring, which is probably the most popular way. Completing the square, as you can see here, most complicated, but the quadratic is the most straightforward, actually. And it may not seem that way when you look at this formula here, but you will see that over time that there's a pretty steady process work with the quadratic. So first thing to look at is the ability to estimate radicals. So one thing that really helps with estimating radicals is if you can tell what perfect square values are consecutive numbers that bookend what's under the radical. So for instance, if you think about root 18, right below it is root 16, and the closest perfect square above it is 25. So square root of 16 is 4, square root of 25 is 5. So we know that this value is somewhere between 4 and 5. Okay, similarly with 45, we know that the square root of 49 is right above it. Square root of 49 is 7, so what square rooted gives us 6? Well, that's 36. So we know that this value is between 6 and 7. Square root of 92, well, square root of 100 is above it. Square root of 100 is 10. So what gives us 9? Well, that's the square root of 81. So we know that this is between 9 and 10. And so on. This would be 25 and 16, so it's between 4 and 5. And this is actually 144, which is 12 squared, and 121, which is 11 squared. Obviously, that maybe takes a little more work as a recollection of what is, for instance, 11 squared, not as commonly used as your 4, 9, 16, 25, and so forth. So what we're going to do with these radicals ultimately is to be able to simplify them. And to simplify them is really to take something like square root of 45, as you see here, and to be able to rewrite it as a whole number and then a smaller value under the radical, which sort of places us in the general neighborhood of what that value is, much more kind of concisely, actually, even though it doesn't look as concise, but it's a little clearer where that value is versus just looking at root 45. And it pulls out the perfect square, which is the key here, so that we ultimately end up with a radical that cannot be simplified any further. So the process of doing this is you find what is the largest perfect square factor of any value, if there is one. Sometimes if we get a value under a radical, it doesn't have a perfect square factor, then basically we've gone as far as we can in terms of simplifying that. But what we do here, and again, finding the largest is just the most efficient. For instance, 16 goes into 48. 4 also goes into 48, but if we use 4, then we're going to have more steps here because we're going to end up having to pull out another 4 along the way. And so it's just a little less efficient for us. So if you can find the biggest perfect square factors, we have 1 and 48, we have 2 and 24, we have no perfect squares yet, but 3 and 16 is also a factor, and so are also factors, I should say, and 16 is going to be then your biggest factor, because again, 4 and 12 is another option, but 4 is obviously a much smaller factor there. So what we're going to do is when we get that 16, we're going to rewrite the radical as the product of two values, utilizing that biggest perfect square value, and then of course whatever it's multiplied by. And in doing so, we can use a little rule with radicals, which is that you can split them into two radicals and just bring the multiplication in between the radicals. And of course, when you do that, now we can take the square root of 16, which is 4, and leave the root 3 as a tag along there. So our final answer is 4 root 3. And again, if root 3 is going to be a value slightly over 1, but not quite 2. So we again have an idea of where this is in terms of this radical. And it's simplified in that we have that 4 out of it. So simplifying other radicals here that, again, are not perfect squares themselves. So we look at, for instance, 52. And with 52, okay, when we look at what factors of 52 we have 1 in 52. We have 2 in 26. What else do we have here? So Let's see, 3 and 14. No, that's not going to work. 3 and so we just continue to look at what goes into this. And 3 times 10 is 30. Nope, we don't have it doesn't go into with 3, so we go on to 4. Well, 4 times 13, like a deck of cards, 4 suits of 13 cards each. That does work. Again, we can keep looking at, let's see, 5 doesn't work. 6 times 8 is 48. 6 times 9 is 54. That doesn't work. 7 times 7 is 49. 7 times 8 is 56. So 4 and 13 is the best we can do. So we are going to rewrite this as 4 times 13, which is root 4 times root 13. So the best we can do here is 2 root 13. With 180, again, we look at what we have. We don't, and again, you can just continue going through these. 3 times 60, none of those are perfect squares yet. We do have a 4 times 45, that does work. We could go 6 times 30. Actually, we have a 5 as well. 5 times, let's see, that would be 36. 36 is a perfect square. All right, so we could use that if we wanted to. Now, if we didn't catch it, let's just say we accidentally went with the 4. So if we wrote this as root 4 times 45, that would give us now square root of 4 times the square root of 45. Well, the square root of 45 is root 9 times root 5. Okay, so what we really have here is, here's square root of 4 is 2, square root of 9 is 3. So we actually have 2 times 3 times root 5, which is, again, now 6 root 5. And this process works just fine if you want to take the roots out one by one. So for instance, as you're going through these these factors, if you catch that 4 and you run with it, again, if you were to go one step further and see that 36 works, well, then you'd have root 36 times root 5, and you'd be right there already. Okay, so it's fewer steps, but again, finding those bigger factors sometimes can be a little trickier. So if you want to take the 4, get that out of there, and now you're working with a little smaller number here in that 45 to see if you have a better chance of catching those factors along the way. So either way works, as long as, again, you end up with 6 times the square root of 5. If you have a smaller number like this, this would be a root 4 times a root 3 in the case of 12, so that's 2 root 3, so that one's a little more straightforward. 240, this one, again, you could go through all of these factors, and you have, let's see, 3 times 80, you have 4 times 60. Okay, so 4 does work here. Now, it does so happen that 15 times 16 is also 240. So you could go that route too, but let's just say we did go root 4, root 60, because we caught that. Well, then we'd have a 2 here, but root 60 would be root 4 times root 15. So now we'd have a 2 here, and now we can't get root 15 any smaller, so our final answer here would be 2 times 2 times root 15, which is equal to 4 root 15, which of course, had we used the 15 and 16, when we take the square root of that 16 there, that would have also given us 4 root 15. So again, find the biggest factor, which is great if you can do that. If you happen to go with the 4, you just got to make sure you keep checking whenever you have another bigger value that may have another perfect square under it, that you do end up catching that. So why did we do that is the question. Well, why we did it actually stems back to that quadratic formula and dealing with roots. And a particular part of the quadratic formulas that we're interested in is right here, which we'll talk about shortly. But again, we had our 3 methods. We had the factoring that we did last unit, very familiar there. There's symbolically, which is, again, just if you have something that's simplified to this point where you just know that it's plus or minus 6. But then the quadratic formula, where we have something like, say, this polynomial right here, the quadratic, and we go through this quadratic formula. Okay, and when we put these values in, so we see that, for instance, b is -5, so a negative b, sorry here, a negative b would be a -5. B is -5, AC are 1 and 6, and again, you just fill that in based off the values in ax squared plus bx plus c, and of course, sometimes those are negatives. So you use those to fill in that formula. Now, particularly with that formula, what we are interested in is this ability to find the value of the discriminant, okay? And the discriminant here, in particular, again, is this part right here under the root, okay? So the discriminant itself, we would then just say in this, as we look at this, is b squared minus 4ac. Not necessarily the root of it, but just b squared minus 4ac. And what's going to happen is if that value ends up being positive, that means we're going to have two real solutions. If it ends up being 0, we're going to have one real solution, which is just where it hits that 0. And then if it ends up being negative, okay, this is negative, then it's going to have 0 real solutions. And at that point, it gets a little more complex. And again, that's in the sense that they are actually literally complex solutions. And so we'll talk about that more down the road. But for now, again, here's just kind of a general layout. So if it equals 0, you have this one rational solution or real solution. If it's a perfect square, they'll actually be rational solutions, meaning that there'll be a whole number or a decimal that doesn't go on forever. If it's not a perfect square, then it will be two irrational solutions. And so we'll look at that as we move forward here. So looking at a couple of examples, when we look at these equations as they're given, we'll zoom in on this here first. So we're going to calculate the discriminant and determine the number of solutions. So right here, we have A equals 6, we have B equals 3, and we have C equals 4. Again, the discriminant formula is B squared minus 4AC. Well, B squared here would be 3 squared. Again, we'll use capital D for discriminant. Minus 4 times A, which is 6, times C, which is 4. Okay, up here. So that would equal 9 minus 96, which gives us a value of -87. And again, negative value means there are 0 real solutions. Okay, looking over at the second one here, again, now we've got an A value that is equal to 3, a B value that's equal to 5, and a C value that's equal to -6. So again, using B squared minus 4AC, we would have now D equals 5 squared minus 4 times 3 times 6. Well, -6 here. Now that negative, of course, is going to be very useful for us here in the sense of getting real solutions, because what we're subtracting then, 4 times 3 is 12. 12 times -6 is a -72. Okay, so if you have a single negative term here, again, keep in mind we are subtracting this whole piece here, and I'll actually put that in a different color. We're subtracting the entire 4AC. So we're still subtracting here a -72, which means it's actually 25 plus 72. Well, that's 97, so we have two real solutions. So you have to be careful here. Again, if A or C is negative, then you're really going to be adding in the end. If they're both negative, well, then they're going to multiply together to be positive, and so you would actually be subtracting still. So just be mindful of where these negatives are. If either one is negative, one or the other, but not both, just plan on being in that situation where you're going to subtract a negative value. Okay, so now we have a situation where the the negative 6x is alone on the other side. So we actually have a little different format here. But again, what we want is for this to equal 0. So in order to get this to equal 0, what we're going to do is I'm going to erase this actually here, because what I'm going to do is I'm going to add 6x to both sides. Okay, and when you add 6x to both sides, that means our formula is actually x squared plus 6x plus 9 equals 0. And again, if you look back on the previous slides, we always have this set equal to 0 because that's how we're going to determine the discriminant and the number of solutions that we have. Okay, so in this case, now a equals 1, b equals 6, and c equals 9. So if it's not given to you all on one side to begin with an a, a b, and a c, you will manipulate that by adding or subtracting from both sides to get it to equal 0. So again, b squared minus 4ac here gives us 6 d equals, 6 squared, because that's the b again, the value with the x, minus 4, a equals 1, and c equals 9. So that is 36. Again, these are both positive numbers, now 1 and 9. So we're actually going to subtract 36 here. And 36 minus 36 is 0, which means we have exactly one real solution. So again, a reminder that the whole rationale for the discriminant is to determine our number of solutions. Okay, so this is just one piece of the bigger quadratic formula that gives us some very important information, okay, about a parabola and its zeros, which in the real world can give us information that about some sort of real world scenario, projectiles or things like that, and when they will actually hit that 0 in terms of a y value. Thank you as always for listening. That's all for now. If you have any questions, please make sure you ask.